Today, I want to go over Dalton's law of partial pressures, both using this law by itself and in problems where you have to use it along with the combined or the ideal gas law. So, Dalton's law just says that the pressure of each gas in a mixture is called the partial pressure of a gas, and that the total pressure of a mixture of gases is equal to the sum of these partial pressures. So you can either have a situation like you think about a scuba diving tank where you have several different gases in the tank, and then the pressure of the mixture of gases in the tank would be the sum of the pressures, of the partial pressures of each one of those gases. You can also think about atmospheric pressure is going to be composed of the partial pressures of the gases in our atmosphere. So in Dalton's law, on the left-hand side of the equation, you can either have total pressure like you have in a tank, or atmospheric pressure like the air pressure in our room. Okay, so if we look at, we have three different gases. If we think about each gas has a partial pressure, so first gas has a partial pressure of 2 atmospheres, the second one has a partial pressure of 1, and the third gas has a partial pressure of 3 atmospheres. If we add these three gases together into a same-sized tank, the total pressure in the tank would be 6 atmospheres. So we would just add these partial pressures together to get this total pressure. That is one type of problem that you'll run into. Another type of problem that you'll run into is a situation where you have a gas collected over water, where you have the water vapor also present. So here we have hydrogen gas collected over water, and it's telling you the temperature which this is done at. So it's telling you that at 22.5 degrees Celsius, the vapor pressure of water is 2.81 kPa. It's also telling you that the atmospheric pressure is 94.4 kPa. So we have our PATM, which we're plugging into the left-hand side of the equation. And then we have our partial pressure of dry hydrogen. And then we have our water vapor pressure. If we subtract that 2.81 from 94.4 kPa, we get a partial pressure of dry hydrogen of 91.6 kPa. When you have a problem like this, it will list the temperature, and a lot of students are confused, like what are they supposed to do with the temperature? Well, in this case, you can just kind of ignore that. This is kind of extra information. However, sometimes you'll have a problem where it will mention water vapor, but it won't give you the actual water vapor pressure. You would then have to look that up in a table which would list the vapor pressures at different temperatures, and that's why the temperature is also given to you, just in case you had to look that up if it weren't given to you in the problem. Okay, guys, so I want you to try some Dalton's law problems before we go into combined and Dalton's. So if you just pause the screencast, try some of those, and then you can start it again to watch when we have the two laws together. Hi, today I would like to go over problems where you'll be using more than one gas law. Specifically, I want to go over problems where you are collecting a gas over water, and this will be told to you in the problem. And as a result, you will have to be using the Dalton's law of partial pressures on top of either the ideal gas law or the combined gas law. To illustrate situations that occur in the lab where it necessitates this, I'm going to show you a video of a reaction which is occurring and where a gas is being generated, and the gas is then being collected over water. So please watch this video.
Potassium chlorate, KClO3, decomposes to potassium chloride, KCl, and oxygen gas, O2, when heated. Manganese peroxide, MnO2, is added to speed up the reaction. The oxygen gas produced in the reaction can be collected by bubbling it through water and collecting it in a bottle or graduated cylinder. As oxygen gas is generated, the gas bubbles rise to the top and displace water from the cylinder. This method of collecting a gas is based on the assumptions that the gas does not react with water and that it is not appreciably soluble in it. The oxygen gas collected in this manner is not pure because water vapor is also present in the cylinder. The total gas pressure is equal to the sum of the pressures exerted by the oxygen gas and the water vapor. Consequently, we must allow for the pressure of water vapor when we calculate the amount of O2 generated. The partial pressure of O2 equals the total pressure minus the pressure due to water vapor.
I'm going to go over a problem now which uses Dalton's law as well as either the combined gas law or the ideal gas law. So when you see a problem where it says it's collected over water, this is telling you that you're going to have to use Dalton's law at some point in the problem. So, and you notice also here it says dry gas. So once you get the pressure of the dry gas by itself. So first of all, we know that we have a volume is 500 milliliters. And we have a temperature is 20 degrees Celsius. It's also telling us that we have a pressure and then it's asking us what is the volume of the dry gas at STP. So we know that our final conditions are going to be temperature is 0 degrees Celsius and our pressure is going to be actually 101.3 kPa. Okay, so that is the same as 1 atmosphere. So that's pressure in kPa STP. So it's asking us what is the volume. So we know that this initial pressure that we have is the wet gas. So what we need to do is we need to get rid of the water vapor. So we need to go to a table, and this is in Google Classroom, of the water vapor pressure. So we're at 20 degrees Celsius when we have the wet gas. So this is our vapor pressure of water. And we need to go down to 20. See that we have at 20 degrees Celsius, we have 2.34 kPa of water vapor pressure. So we're going to take this and subtract 2.34 kPa to get our dry gas. So we have 96 minus 2.34, and that gives us 93.66 kPa. And with these kind of problems, I don't worry about sig figs, just because if we were to think about sig figs, we would lose some information here before the end. So just at the end, think about sig figs, but don't worry about sig figs at this point. Okay, so we have two sets of conditions. So we're going to be using the combined gas law. P1 V1 over T1 is equal to P2 V2 over T2. Okay, so now we're going to be comparing a dry gas to a dry gas. So we have to make sure our temperatures are in Kelvin, just like before. So this gives us 293 Kelvin and 273 Kelvin. So we have our pressures, so let me write this down here, of 93.66 kPa times our volume. And then we have our initial temperature, 293 Kelvin. And then we have our final pressure, which is 101.3 kPa times V2, which we don't know. And then our temperature, 273 Kelvin. Okay, so we're going to cross multiply, and you notice Kelvin's on both sides, so we can get rid of that. We have kPa on both sides, so we can get rid of that. And we're going to get V2. So we're going to get that is equal to 273 times 93.66 times 500 over 293 times 101.3. Okay, so let's plug that into our calculator, and we get 273 times 93.66 times 500. Divide that by 293 times 101.3. And that gives us 400, and I'm going to do this in 2 sig figs, because actually 3 sig figs, because when we add 20 to 273, we get 293. So it's 431 milliliters. So that is our final volume. So you need to do this kind of problem when you see that collected over water, so you have to incorporate the Dalton's law at some point. Okay, so let's look at one other problem on here. This is slightly different, but what we have here is we have two containers. So we have a 400 milliliter container with oxygen and 200 milliliter container with hydrogen. So these are separated by a valve. So just imagine we have a large container connected with a valve to a smaller container. So the large container is 400 milliliters. Let me separate it with a valve with oxygen. And this one is at 53.3 kPa. The smaller container is 200 milliliters. And this one has hydrogen, and it's 93.33 kPa. So when we remove this valve, when we open this valve, what we have is we now have a larger container, which is 600 milliliters. So we actually have two Boyle's law problems, because we can assume these are at the same temperature. So temperatures being held constant. So we have one Boyle's law problem with initial volume of 400 milliliters, initial pressure of 53.3 kPa, and a final volume of 600 milliliters, and an unknown pressure of our oxygen. And then we have a second Boyle's law problem with 200 milliliters. Our initial pressure is 93.33 kPa. Our final volume is 600 milliliters, and our final pressure is unknown. And again, this is our pressure, our partial pressure in this case of oxygen, and this is our partial pressure of hydrogen here. So we're going to solve these two. So we have Boyle's law, P1V1 is equal to P2V2. And then we have 400 milliliters times 53.3 kPa is equal to 600 milliliters times P2. So we isolate P2. We do the same thing with this one. So we have 200 milliliters times 93.33 kPa is equal to 600 milliliters times P2. So again, we isolate P2. Okay, so let's solve each one of these. So we have 400 times 53.3 divided by 600. Okay, so our first one, P2 for the first one, is 35.53 kPa. Our second one is 200 times 93.33 divided by 600, and that one would be 31.11 kPa. Let me just cancel out our units. And then we add these two together. So this is what makes this a Dalton's law problem. The total pressure of our container will be the sum of the partial pressures of the hydrogen and oxygen gases. So we're going to do that plus 35.53. And that gives us PT is 66.64 kPa. And we're going to round this to 3 significant figures, so it's going to be 66.6 kPa is our final answer. Okay, so good luck on these problems. Make sure you're using your vapor pressure table. I would say most of the problems need to use that. And just make sure you're paying attention to your units. So good luck.